All right, so the last time we met, we were talking about significant figures. And we looked at some values and we identified how many significant figures there were. And, this isn't terribly critical. It's something to keep in mind and have a general understanding of, but you're not going to have a lot of test questions, maybe one out of all of them that will ever say, what's the correct number of significant figures? It's, again, more than something that just kind of distills on you and you gradually understand and kind of recognize its place. One reason why it's just not that important is because when you're doing your calculations, it's important to know what your final number is, but it never really limits your performance in the lab or anything like that. It's really in the write-up, and it's going to be a long time before most of us are writing up papers that are important for any reason. So in your lab write-ups, that's where you want to start kind of beginning to write them up and stuff, write up with significant figures. But we have to have a conversation about how you identify the appropriate number of significant figures when you're multiplying two values together, or when you're dividing values together, or when you're adding or subtracting values together. And so that's what we're going to talk about right now. So here's an example. If I put in my calculator 3.14 times 2.751 divided by 0.64, then the answer that the calculator says is 13.49709375. All right? But when we report the number, we want to let the other scientists who are going to be reading the value have a feel for the accuracy of the number. And so we want to make sure that we have the correct number of significant figures reported. So again, if I write 13.497, for example, I'm telling the person who is reading this number that these numbers were known and that one is my what? Do you remember?
I can't see what you wrote there.
You can't see that? Is it really small?
No, I don't see it at all.
Oh, you can't see my screen? Oh, nuts.
No, I see your screen. I see you, but you're not looking.
Again, 13.49 are significant digits, but the 7 is what? Do you remember if my last digit is what?
Was it an estimate?
That's right. It's my estimate. Excellent. So that's what we're trying to tell somebody when we write down the value. Now, which number should I choose as my estimate if this was these were the measurements, the numbers that I was given before? 3.14, 2.751, and 0.64. The 3.14 has 3 significant figures. You see that? The 2.751, how many significant figures there?
2.
The 2.75.
I mean 2.
No.
Well, 75 is the significant number.
So we got
2.751.
751. So all 4 of those are significant digits.
Oh, they are?
Yeah, all 4 are significant. Down here, the 0.64, 0.64, that's 2 significant figures.
Right. Okay.
So when I have, oops, I got to get this fan going on me here. When I have 3 significant figures times 4 significant figures divided by 2 significant figures, the question is, how many significant figures should my answer have? And the answer is, we always have to go with the fewest, because our weakest measurement, which means our least sensitive measurement, has to limit all the others. Okay? So the answer here has to have only 2 significant digits. And so then I come up to my number that I have from the calculator, and I look at those significant digits. 1, 3, that's 2 right there. So then I have to round to that second significant digit. So then I can look to the right, and if this was a 5, then I could put 14, but it's not a 5 or higher. It's lower than 5. So I'm just going to be able to include 13. 13. So my answer is 2 significant figures, and the answer is just 13. Okay? Very good. Now, if I look at this problem here, 12.33 times 0.00002, I need to determine how many significant figures I should have in my answer. Now, note that this answer here is not looking for the answer, right, to the problem. It's just asking how many significant figures should be in the answer, right? Okay, so what do you think? How many significant figures does this number have right here, the 12.33?
4.
4. Very good. Now this one's a little tricky, 0.00002. How many significant digits?
1.
It's 1. That's right. It's just 1. So if I have a value that has 4 significant digits and I multiply it by a value that has 1 significant digit, how many significant digits should my answer have?
Well, none of the. It should have 1, right?
That's right. Very good. Should have only 1 significant digit there. Okay. Very good. Excellent. So now what we're seeing is when you multiply or divide or any combination, multiply, divide, multiply, multiply, divide, and then you get your answer, the number of significant figures that your answer should have will be limited to the measurement that had the fewest number of significant digits. Okay? Now, what about adding and subtracting? Adding and subtracting, we do something a little bit different. Okay? When we add and subtract, we take our values that we're going to add or subtract, and we line them up like they're lined up here. We line them up with the decimal places all lined up. We put them in the calculator, get our answer, and then after we get our answer, we identify which one of the measurements had the fewest or the lowest sensitivity, which is which one of these has the fewest number of significant digits to the right of the decimal point. And see how this one stops right here? It doesn't have any value here. So this estimate right here is going to limit all of the other measurements because we don't know what was down in these measurements here or in these decimal places here that could have added to these. So we get our answer, and then we have to round to this point. So in this case, the answer is 169.8 because it has to round to that point. All right? Now, a lot of people confuse multiplication and division with addition and subtraction. And because multiplication and division is pretty straightforward, you just find the one that's the least, and that's the number of significant digits that your answer has to have, then that's so it's easy to remember. It sticks in your head better than this one. People get lazy and they don't line up the problems. They don't line the numbers. They don't line them up, and then in the end they just look and kind of guess, right? So make sure you always line them up like that when you have to answer these types of questions. So here we go. How many significant figures will result from this problem? 10.33 minus 0.0344. All right. So if I bring out my calculator here and I put into the calculator 10.33 minus 0.0344, all right, I get my answer 10.2956, but I might not be able to visualize just with that information where I need to round my answer to. So because it's a subtraction problem, what we really need to do is we need to write it down, 10.33 minus 0.0344. I lined up my values there. I have my answer here, 10.2956. I write that down there, lined up as well, 2956. Okay. Now, where am I going to cut off the answer? How many significant figures am I going to cut it off at?
Right after the 29.
That's right. So right here, because that's where my limit is there, I have to round this number there. I look to the right. Does it round up or down? Up. So it's going to be 10.30. All right. And now again, the question isn't asking what the answer to the problem is. It's just asking the number of significant digits. So how many significant digits do I have there?
Well, 3, right?
I do have a fourth because that 0 was my estimate, right? So this last one is whatever the last one is there. If it ends up needing to be there,
Okay.
yeah. So the answer would be, like you said, 4 significant figures. Okay, good. Now, here's another problem we can do. Practice. We have 10 times 10.88 minus 12.2 divided by 2.2. Now, this is a mixed multiplication, division, addition, or subtraction problem, right? So we have to follow our order of operations, which would mean we would do this multiplication inside the parentheses first. We would do this subtraction here, and then we would divide by the 2.2 at the end. All right? Now, when you go back and forth between multiplication and division and addition and subtraction, you always need to stop and gather your significant figures before you shift over. So the first thing we're going to do is our 10 times our 10.88. All right, so if we do that problem first, 10.0 times 10.88. All right, our answer, I can put it in the calculator, it'll be 108.8. But how many significant digits should this answer have? 3. That's right, because this is 3 sig figs. That's short for significant figures. And this is 4 sig figs, right? And so we have to round it to the third significant figure, which is going to make this 100 and what? 108.8. We're going to round it up to 109. 109, right. Okay, so now the next step is to take 109 and subtract 12.2. So I'm going to make sure I line it up, right? Don't need to spend any extra brain power. 109 minus 12.2. I'm getting 96.8. 96.8. All right. How many significant figures, or where should I round to? It looks like I have 3 significant figures here and 3 there. So you might say, well, I'm supposed to have 3 significant figures in the answer. But that's not how it works with subtraction and addition, right?
We're going to round that to 97.
97. That's right. That's where our cutoff is, right there. So it's going to round to 97. So then we have the last part of the problem. And again, each step, we had to gather our significant figures only because we went from multiplication to subtraction and then back to division. All right? If all of this was just multiplication, division, we wouldn't have to gather significant figures until the very end. Okay? So 97 divided by 2.2. All right. I can do that in my calculator. Got 44.0909. Okay, so how many significant digits am I going to keep?
Just 2.
Just 2. That's right. 2 significant digits in each of those. It's a division problem. So the answer is 44, and that has 2 significant digits. So our answer that they're looking for here is 2. Okay. Wonderful job. So,
I have a question.
yeah.
So going back to the slide, yeah. So is it just a coincidence that since we're looking at the denominator,
Yeah.
the 2.2 is 2? Was it just a coincidence that the answer is 2? I mean, can we use that as a shortcut, or is that just?
It was definitely, because you saw this here, you knew that the answer wasn't going to be more than 2. But we didn't know if it was going to be 1, right?
Oh, I see.
So it was possible that this business up here, especially if we subtracted enough that we went down to a single significant digit, it would be possible that the answer would just be 1 significant digit.
Oh, okay.
But you're right. When you saw that 2.2, and maybe you knew that division was going to be the last thing we did, you knew that the answer was not going to be any more than 2 because of this only having 2 significant digits.
Okay.
Good. Now I'm going to introduce to you something that we call conversion factors. Conversion factors. Conversion factors are helpful tools. And what a conversion factor is it's essentially another way of saying the number 1. The number 1. And if you multiply something by 1, you always get that same number back. If you divide a number by the value 1, you always get that same number back. And so if we can construct what we call these conversion factors that are equal to 1, meaning what's on top is the same as what's on the bottom of a fraction, then we can use them to answer lots of questions, and they can lead us to the answers even though we don't know how to answer the questions. So the conversion factor becomes very valuable. Again, if you have a problem, now what's a problem? A problem is something you don't know the answer to. If you know the answer, it's not a problem, right? It only becomes a problem when we don't know the answer, when you don't know how to find the answer. And that's the problem, right? And so when we don't know what the answer is, we don't know how to find it, we need to find a way to help us overcome that. That is solving problems, right? It's not solving problems if you can just look it up on Google and find the answer, right? We have to move into a different realm, solving problems. So these conversion factors are critical for us for that. Sometimes we can solve the problem, but there's just too many steps, and our mind can't work complex. It's not complex enough to answer those. And so we, again, piece it into little pieces. Now, there's many ways that we can write the number 1. If I put 2 over 2, that's equal to 1. 3 over 3, 6 over 6. Any number over itself will always equal 1. So what about the number 1 over 12? Would that ever equal 1? Not just as the numbers are, but if we gave them units like this, 1 foot over 12 inches, then you could say, yeah, that's the same thing. That's the same thing. And then that becomes helpful to us when we have to answer problems like how many feet in 653 inches, right? And some people just say, oh, you multiply by 12, or you divide by 12, or you take 12 and divide it by 653, or take 1 times 653 divided by 12. Some people, it's in their mind already. And they'll find these exercises, especially the next handful of slides, kind kind of frustrating because they say, oh, you just do this, you just do this, you just do this. But that's all right. We're not teaching necessarily what the answer is. We're trying to get us into a mindset where, because if you know the answer, it's not a problem, right? We're trying to get ourselves into a mindset where there's a problem. We don't know the answer. We don't know how to approach it. But now we have a toolkit that will allow us to approach it, even if we don't know the answer. And gradually, as we get closer to it, we say, oh, yeah, I can figure that out. Okay? So we use an answer question like this to kind of train ourselves for that. So don't get frustrated if we don't if we seem to be going slow and talking about stuff that's silly. So how many feet in 653 inches? The way we would answer this is we would say, okay, I know my conversion factor. I know that 1 foot is the same as 12 inches. Or I could say also 12 inches is the same as 1 foot. So every time you get some sort of a relationship, or a relationship like feet to inches, there's 2 conversion factors that you can get. All right? And then from this information, if I know I have 653 inches, but I want to know the number of feet that is, I'm in inches, I need to get to feet. I know I need to get the inches to be gone. So I need to put inches down here, and then I can put feet up there. So then that shows me the conversion factor that I need to use. I have 1 foot, 12 inches, and then I can see taking this number and multiplying it by this fraction would be the same as taking 653 times 1 divided by 12, and then that'll give me my answer. And so, most of us knew you just have to divide by 12. But we won't always know that for a given problem. This isn't a problem. We already know this. But this is how you need to be able to set it up. And having the ability to set up your problems in what we call, this is called dimensional analysis, and we'll introduce it again and again, and we'll encourage you to use it. I mean, you have to know and learn how to use this as a tool if you're going to be able to answer any question that comes at you, right? And it's also a blueprint, a map, evidence. It's how you can see and show somebody, look, I know this is how you answer the problem, because you can see what happens to the units. Inches divide out, and feet are left over, and that's what we want our answer in. All right? So whenever there's a question, hey, how do you do this? How do you do that? If somebody can provide a map, the blueprint, the evidence for how the problem's done, then everybody knows. You can just see it and say, okay, you're right, because I can see that the units are doing what we want them to do. All right. So, conversion factors. We can write lots of different conversion factors. Here are a set of conversion factors. Now, one of these conversion factors is not correct. And, an example of a conversion factor that's not correct, example of when we might make a mistake is like when I say, okay, yeah, I know, it's inches to feet. Yeah, that's no problem. 12 to 1. I got it, right? And then you move forward because you're in a hurry, right? What's wrong with the conversion factor here?
One inch to 12 feet.
Yeah. Is that a problem? Yeah, it's not 1 to 12. It's supposed to be 12 to 1, the way I have it set up there, right? So, and that's a very common mistake. People would say, I would never do that, but that's a very common mistake. So, can we look at these conversion factors here and identify the one that is incorrect? Incorrect. These are a little bit, we're not maybe as easily familiar with, for example, kilograms to milligrams, kilograms to grams maybe, but to milligrams, that's a little bit harder. But I think the one that's incorrect should be able to stick out to us.
Okay.
Any ideas?
Oh, yeah.
How about this 2.54 centimeters to inch? Does that sound right? Or should it be 1 inch for 2.5 or 1 centimeter for 2.54 inches?
Oh, that's right. Yeah, you're right.
Well, not necessarily. I'm just asking.
Wait. No, that's right. 1 inch is
Yeah, that's right.
an inch bigger. Yeah.
Okay.
Now I'm looking at the. I'm looking at the. Okay, it's between the 1,000 millimeter over 1 meter and the 1,000 liters over 1 milliliter. One of those has to be. I'm saying it's between those two, right?
Okay.
Or am I completely off? Is the answer in one of those?
Well, we don't want to give the fun away. Let's try to think about it, figure them out. So this one up top, 1,000 millimeters in 1 meter. We have, a meter. That's about that big, right? Is that true? Is that 1,000 millimeters? Is that fair to say or no? Or at least we can't rule it out because a millimeter is the
Millimeter, yeah, right.
tiny thing. So could there be 1,000 in there? Maybe. The 1,000 liters. Are you familiar with a liter very much at all?
Yeah, when you go, it's almost a gallon.
Okay.
Equivalent. It's the soda bottles come in 3 liters.
All right. Very good. So how about a milliliter? Are you familiar with that? Is that smaller or larger? Huh?
Smaller.
So are we saying that this one isn't correct?
So, yeah, well, it's reversed, right?
Yeah, that's right. Very good. If I had a liter, that's, a third of a soda pop or half a soda pop, right? Big bottle. That would be about 1,000, or not about, it's exactly, right? 1,000 milliliters. Very good. So, we found the incorrect one.
So what was confusing me is okay, up on top, right?
Yeah?
We have 12 inches over 1 foot, and we have 1 foot over 12 inches.
Yeah, we didn't change the numbers.
Okay, but then solved, it says equal to 1. I'm sorry, you're going to have to explain to me why. I guess it's the same as what you were talking about, using that if we're in a hurry and we accidentally put down 1 inch or over 12
feet.
Over 12 feet. Right?
Yeah. And remember, I can restate this conversion factor, 1 liter over 1,000 milliliters, as 1,000 milliliters over 1 liter. Right?
Okay, that's what I'm getting at, right? You
Yeah.
can do that.
Yeah.
So, show me, enlarge the graph again. Where was I?
Well, there's the 12 inches per foot, and this is just flipped. We didn't flip the numbers only. We also flipped the units so that
Right.
1 foot is on top and 12 inches is on the bottom now.
Okay.
So both of those are good conversion factors.
Okay, and show me the paper one more time. I just have to.
Well, these are examples of the correct conversion factors. 1,000 milliliters over a liter, those are equivalents, or 1 liter over 1,000 milliliters, right? So milliliters on top, liters on bottom down here. Over here, liters on top, milliliters on bottom over there. Okay, very good. So, now here's an example of a problem. I can't go on the big kid rides at Euro Disney until I reach 1.1 meters. How tall is that in feet? Okay, so we have 1.1 meters, and we need to get to feet, and we need to use conversion factors. All right, so now I'm going to introduce to you not just the conversion factors and how to identify the correct conversion factors, but I'm going to introduce to you a method that we want to get comfortable doing. Okay? We want to get comfortable following this method because it lays a blueprint out for us that we can see to answer this type of a question. And here's what we do. The first thing we do for this type of a question is we write ourselves an equal sign. An equal sign off to the right side of our paper. And then we draw a line. And while we draw this line, we breathe out. Right? And what that does for us is it puts our mindset in a confident position. We just did something that took no brain cells, wasn't hard to think about. And now we're going to do a few other steps that take no brain cells, but what they're doing is they're preparing our map so that when we're done, we'll be able to know that we have the right answer. There'll be no doubt. The next thing we do is after we draw this, to the right of our equal sign, we write the units that we're after. Now, can you look at this question and find out what the units are that we want to have to the right of our equal sign?
Feet.
Feet. That's right. So we write feet there. Doesn't take very many brain cells. Sometimes it's hard to get there and takes a couple. But in general, that is probably a very minimal amount of brain cells. And then we start with our first little section up here to the top left. And we're going to put the number that we start with. The number that we start with. And in this case, can you tell which number we start with?
Yeah, the 1.1.
And we also want to get the units. So what are the units?
Meter?
Yeah, 1.1 meters. Very good. So, again, this didn't take a whole lot of brain cells, right? So we've got everything pretty easy for us to do. We also are in a situation where sometimes you can put different numbers here that are provided in the problem and still get to where you want to be. So don't ever get stressed about just choosing something to start with, right? Additionally, we're learning. We're learning. And so part of learning is trying the problem and then starting over if you don't get it. Too many people are afraid of thinking like it's a piano song or something, that you have to start and finish without any mistakes. And if you mess up, you just go back and you have to start over. And so they're afraid, oh, I don't want to start over. I have to do it perfect. But that's not how you learn how to play the piano. That's not an effective method for solving problems. Frequently, you have to start over. But it really requires no brain power. It just requires a little more paper. But the paper is willing to sacrifice itself so that we can learn. So we just start over if we need to. So it's not bad to start with just something and then find out, nope, didn't work. And then we have a map. We know it's the wrong one, that we can kind of copy most of it or give us an idea where to start from there. One more piece of free, non-zero brain cell information. I know that I don't want meters as the final answer here. So I know that my units down here have to be in meters. So I can put that down there for free. All right. So everything that I have written up there, and I'm trying to write a map that shows me how to convert my 1.1 meters to feet. Everything I have written up there right now was minimal number of brain cells. Pretty straightforward, pretty free. Okay. So now I have to think of some conversion factors, and this is where our brain cells come into play. Conversion factors that will get me from meters closer to feet. And I've supplied some up here for us to look at. Which one of these looks like something we might be able to use to get us closer to feet?
Going from the meter?
Yeah. Has to have meters on the bottom, right?
Right. So it's the centimeter to be
Meters to centimeters?
well, let's see, because we got 1 centimeter, 100 meters, 100 centimeters, 1 meter. Yeah, I guess they're.
So let's think about
Yeah,
it.
I just confused myself.
Let's think about it. Let's say we want to go to centimeters.
Okay.
Now the numbers have to reflect the appropriate answer or appropriate value. How many centimeters are there per meter?
Okay. I can't read that chart. But
Well,
was it 250?
no. How many centimeters in 1 meter? Remember the centa prefix is the hundreds, right?
It's 100, right?
Right. So where do I put the 100? Do I put it down here with the meters or up here with the centimeters?
Up on top.
Okay. 100 centimeters for every 1 meter. Okay. Very good. So that was a significant amount of brain power, right? And now we get a freebie. We know our next one has to have centimeters on the bottom. Do you know how we know that?
Yeah.
Because we need to cancel
We have
those centimeters.
centimeters on top.
Yeah. So where would we like to go?
So we want to do inches.
Yeah, let's go to inches. Let's go to inches. What do you think? Do you remember how many centimeters per inch or inches per centimeter?
I think it's 1 inch is 2.5 centimeters.
That's right, 2.5, and then we had the 4 there as well, 2.54. Very good. Now I'm in inches. What goes down here?
The inch.
Yep. And what goes up here?
The feet.
Feet. We know, we did these in little pieces that we knew. We knew centimeters to meters, we knew centimeters to inches, and now we know inches to feet. Okay? So 12 and 1. Is that right?
No.
I messed up, didn't I? Good, you caught it. 1 foot is 12 inches. Excellent. So then, move that up there, and I'll bring in my calculator here, and I will try to find out what the answer is, doing the math accordingly. Okay? So here's what we find. If I take, there we go. If I take 1.1, multiply it by the 100, whoops, forgot to put in the multiple sign, times 100, times the 1, times the 1, divided by the 1, divided by 2.54, divided by 12, and then I get 3.608923885. How many significant figures did I start with? 2. So how many significant figures is this answer going to have?
Just 2.
Just 2. So I got 3.60, so it's going to round up to just 3.6. Okay? Did you follow that?
Yeah.
Okay, let me show you a few more things here. I'm going to do it again. This time I'm going to do it different with the numbers. I'm going to put 1.1, and this time I'm going to divide by 2.54, and then I'm going to divide by the 12, and then I'm going to times by the 100, and then I'm going to, actually I'm not going to times by 1, I'm not going to times by this one, I'm not going to divide by that one, and I'm just going to push enter, right? And I get the same answer, right? Now, why didn't I change the answer by multiplying by these 1s and dividing by that 1? Because we know, you multiply by 1, you divide by 1, you don't change the value, right? How about this? What if I start with the 100 this time, divide by the 12, then divide by the 2.54, and then times the 1.1? I get the same answer, right? So it doesn't matter the order, just as long as it's on top, it puts a multiplication in front, and if it's on the bottom, we put a division in the bottom, in front, right? Okay? So that's a little reminder from our algebra days that what we say is that multiplication and division, they commute. It doesn't matter the order that you perform them in, you're going to get the same answer. And also, multiplying by 1 and dividing by 1 is an identity. It doesn't change the answer. Okay, very good. In terms of units, just a reminder, meters were canceled out because we divided by meters. Centimeters were canceled out because we divided by centimeters. Inches were canceled out. Feet are left. We didn't do anything with them, and that's what we wanted in the end. Okay, excellent. So that's a good place to stop for now. We're learning to use conversion factors and solve problems. And when we come back next time, we'll try some more practices with this, and we'll get lots of practices. Now, don't get complacent and say, oh, I already know how to do that. You just divide by this or multiply by this, because we're practicing with the easy ones to try to learn the method. Okay.